Folks. So I wanted to go over this question from section 4.7 just to give you another example of working through an optimization problem. So the problem reads as this. So a farmer wants to fence in an area of 1.5 million square feet in a rectangular field and then divide it in half with a fence parallel to one of the sides of the rectangle. How can he do this so as to minimize the cost of the fence? Okay, so I actually tried to make an effort here to not really think about this question before really recording this video, so that what you're seeing is really authentic, me actually going through the problem solving process. So the first thing I'm thinking is, okay, rectangular field, I'm gonna draw a rectangle. So I'm gonna draw, actually I can do this sort of in a fancy way using, there we go. I don't want it to be colored in though. Okay. So, okay, so I have a rectangular field, and then I also have to divide it in half with a fence parallel to one of the sides. Okay, so I need to sort of draw then a little line that is roughly in the middle. Okay. And I want to minimize the cost of all this fencing. Okay, so let me give some variable names right away. So maybe these lengths are all X, right? They all have to be the same length. And then maybe the long side is Y. Okay, so that's Y. And of course, this is Y as well. Okay. And so, okay, if I go back to read the problem, it says, okay, I want to fence in an area of 1.5 million square feet. Okay, so I know the area is, okay, 1.5 million. I have to add, how many zeros do I need? I need one more zero. Okay, 1.5 million. Okay, that's the area. And that's, right, the area is X times Y, right? That's the total area that's enclosed. And then what else do I need? How can I do this so as to minimize the cost of the fence? Okay, so I have a goal, right? My goal is to minimize the cost, right? The cost of the fence. But okay, there's no, what is the cost of the fence, right? The cost, I would interpret that as the total perimeter, right? I mean, the cost of the fence should be the amount of fence I need, which in this case should be the perimeter. So this should be equal to the amount of perimeter of the shape. Okay, and so I can actually write that down, right? The perimeter P of all the shape, well, if I count up all the side lengths, I have 3 X's plus 2 Y's. Okay, so it's not your typical perimeter of a rectangle, right? I have that middle line, which gives me an extra X. Okay, so, and that's my goal, right? Is I'm going to minimize P. Okay, minimize P. So, okay, right now P is defined in terms of X and Y. So I should use my area formula to rewrite it in terms of only a single variable. So let me solve. So let me solve 1.5 million. These numbers are not super friendly to work with, equaling XY. I'm going to solve this for Y. So I get 1,500,000 over X equals Y. And I can now plug this back in, right? And I can plug in the P equation, the perimeter equation. So that gives me the perimeter P equals 3X plus 2 times Y. I'm replacing with 1.5 million over X. Okay. And so what does that give me? Perimeter equals 3X plus, now if I multiply, I'm going to get 3 million. These numbers are a little bit unfriendly. Okay, make sure I don't make a mistake here. All over X. Okay, so I have now written my equation P in terms of a single variable. P is the thing I'm looking to optimize, so this is good. So all I need now is sort of a range of X, right? So X is between what and what? So, okay, so certainly X is bigger than 0. Right? So between 0 and, how big can X be? Well, there's no obvious upper bound, right? Because I could make X really, really big and then Y would be super duper tiny, but that's totally legitimate. So since I don't have an obvious way of bounding X, let's just say X is between 0 and infinity. So because X is between 0 and infinity, this is an infinite interval, which means I'm not going to be using the closed interval method to solve this, right? I'm going to be doing a number line test, right? The first derivative test. Okay, so it's going to be a first derivative test in order to actually check my critical ahead then and optimize this P. So P prime of X equals 3. So 3X becomes 3. And then minus 3 million over X squared. Okay, now how did I get that, right? So you might be a little, but that might be a little fast, right? So you might be a little confused. I'm looking at what's the derivative of 1 over X. Okay, I'm leaving the 3 million just alone, right? It's a constant. And the derivative of 1 over X is the same thing as the derivative of X to the minus 1, which is minus X to the minus 2. Okay, and so that's where the minus 1 over X squared came from. Okay. So now that I have this, I should find my critical numbers. So first, where P prime of X equals 0, and also where P prime of X does not exist. Okay, so where it equals 0, I get 3 minus 3 million over X squared equals 0, which I can write as 3 equals 3 million over X squared. 3X squared equals 3 million, or X squared equals 1 million. Okay, so X equals, let's see, how many zeros do I need? How does this look, right? 10 to the, okay, so in my head, I'm doing a million is 10 to the 6. So the square root of that is 10 to the 3. And so I need 3 zeros, right? Okay. So X should be 1,000. And that's one of my critical numbers. And then places where the derivative does not exist. Well, I notice I have some, if I write down the equation, right? I have some issues with X equaling 0. So there's like some division by 0 issues. And I don't really have to include this, right? Because I'm not really, I know that X equals 0 is not a legitimate number to plug in, right? I can't plug it into my original function. Okay, so I can ignore this. This is irrelevant. So I only have one critical number, and that's 1,000. All right, let's see if this is actually the minimum. So I should do my number line test to check. So plugging in X equals 1,000 into the derivative. Okay, well, that gives me 0, but I want to check numbers close to maybe, so 0. So I plug in a number very, very close to 0. Right, plug in a number very close to 0. What do I notice? I notice that I'm doing 3 minus 3 million divided by, okay, a number super close to 0. So what's that going to do? That's going to make this number even bigger, right? So this whole thing should be a huge negative number, which means my derivative is a huge negative number. Okay, so this all over here should be negative. And over here, if I plug in a number like, say, 10 to the 10, all right, what's happening over here? Now, when I plug that into my derivative, I'm getting 3 minus, now I have 3 million, sure. I'm dividing it by, let's say, a humongously huge number. And so that makes this overall really tiny, right? You might say, well, 3 million is really big. Yeah, but I can make X even bigger, right? So I can make this really, really tiny, and I get 3 minus a tiny number. So it should be like 3 or 2.9, but in any case, it's positive, right? So over here, I get something positive for sure. And so what do I end up with? Well, I end up with a little shape that should be decreasing and increasing, which means this is a minimum. And that's good, right? I wanted to say that I was minimizing cost, minimizing P. Great. That's what I was aiming for. And so, yeah, what do we get? Well, so we know X equals 1,000. And what is that going to be? Feet. what's my units? Yeah, feet. So it's 1,000 feet. And y, I can solve for, right? The other dimension that I didn't know is given by 1.5 million over x. So I can quickly solve for that. So y should be 150000000. Oh, maybe too many zeros. Oh no. So 1500000. There we go. Over 1,000. Let me be kind of careful. Cross out 3 of the zeros each, and I'm left with 1,500 feet for y. And so if I take these dimensions for my fence, I will enclose 1.5 million square feet and also minimize the amount of fence I need to use. All right. Interesting question. Somewhat annoying calculation, right? To be very thoughtful, but that's good, so, right? Keep my brain awake. So hopefully this was helpful and a new example that you can add to your arsenal. And if you have any questions, definitely let me know.